Mr. Bondi back here again with our next lesson, continuing with macromolecules, this time on lipids. And so we have an image here that shows several varieties of foods that are high in lipids. And again, lipids are oftentimes called fats. And so if you take a look at the food items that we see here, a very common source of fat is animal protein or animal meat, in this case, this fish. We also can find high levels of fat in these avocados and nuts and then these oils as well. These are all good sources of fat that we can find from our food. And this is just one of the types of lipids. Another type of lipid are waxes. And of course, we use waxes for a number of things, but clearly candles is another one. Wax can also be used in a number of different industrial applications as well and can kind of help as a lubricant. And then finally, oils are another major type of lipids that we use on a regular basis. Specifically, I'm referring to oils of the type that we consume: vegetable oil, canola oil, olive oil, things like that. So when we talk about all of these different lipids, they all have a few things in common, and it's that they're afraid of water, or a term that we call hydrophobic. So when we take that term and we break it apart, the hydro part is referring to water, and the phobic part means to fear. So really what you end up having here is a chemical compound that is afraid of water. So over here on the right, I have an image of a glass of water with some oils floating on the top of it. And if I were to ask you, why is that oil floating? Most often people would come up with an answer of like, well, the oil is less dense than the water. And that is absolutely true. But then the question becomes further, why aren't they mixing? Because if I took the oil out and I added in another substance, let's say, for example, a solution of ethanol, which is a type of alcohol, it has a different density than water, but would definitely mix and dissolve within the water. So why doesn't the oil? And again, the density is making the oil stay on top, but it doesn't prevent it from mixing. So let's take a look at the chemistry of water, and we can get some of our answers from this. So here's a water molecule. We can see here's the oxygen, and then here's one hydrogen and a second hydrogen. So H2O, this is a water molecule. What's important to remember about water is that water uses a type of chemical bond that are called covalent bonds. But more specifically, it uses something that we call polar covalent bonds. Now, polar covalent bonds are still a type of covalent bond. Remember that in covalent bonds, electrons are shared back and forth between atoms. They don't pick up and move and permanently stay on one atom, but they move back and forth, which creates the attractive force. In a polar covalent bond, though, one or more of the atoms become a little bit greedy. What I mean by that is that the electrons will spend more time around that atom than they will around the others. This is referred to a property that's called electronegativity. Oxygen, in this case, is the greedy one in water. And so what will end up happening is the electrons will spend more of their time around the oxygen atom and then less time around each hydrogen atom. That creates some unique properties, remembering that electrons are negatively charged, meaning that if the electrons spend more time around oxygen, that's going to make oxygen negative, or in this case, slightly negative. It's not a full -1 charge because remember the electrons are moving back, but they just spend more time around oxygen, making oxygen slightly negative. So if oxygen is slightly negative, that means that each hydrogen atom then has to be slightly positive because the electrons are spending less time around it. If you have less of a negative charge, it means you're more positive. So then each hydrogen atom gets a little bit of a positive charge. So what we end up getting is this separation of charges, where you have a negative charge on one end and a positive charge on the other, kind of like that of a magnet, where you have the separation of the two ends, the north pole of the magnet and the south pole of the magnet. What that creates is what we call poles. The ends of magnets are called poles. And so the ends of these chemical compounds also have poles, hence the term polar covalent bond. There's a negative pole and a positive pole. Where this really comes into play is when we take a look at when we have multiple water molecules all together. Because you think about it, water is never in just one individual molecule by itself. There's millions and millions of them all together. Well, these slight charges create unique interactions between the separate water molecules. Let's take a look at this image. There's 3 water molecules. Here's one, here's a second, and here's a third. The solid lines are indicating the polar covalent bonds. These are things that are strong chemical bonds. Notice how there's this symbol here with a little negative sign. This is the symbol for a partial negative charge, not a full negative charge. And this is the symbol for a partial positive charge. So let's start by looking at this oxygen and this water molecule right here with its slight negative charge. Well, opposite charges are attracted to each other. So this negative charge has a very slight attractive force, which is shown by this dashed line right here, with this positive charge of a separate water molecule. What that does is it creates a very small but significant attractive force between these two separate molecules. It makes these water molecules almost want to stick together, as it were. And there's a name for this slight interaction. It's indicated right here. It's called hydrogen bonds. And it'll happen between several, if not all of the water molecules will have these slight interactions, which keeps the water molecules very close to each other and creates some really unique chemical properties for water that we'll get into a little bit more later. Well, the other type of covalent bond is a nonpolar covalent bond. And in the name, what it sounds like, there are no poles. And the reason why there are no poles in these nonpolar covalent bonds is because the electrons are shared evenly. They spend equal amounts of time around each atom. So in this case, we have a chemical compound of methane. And there's a carbon with 4 hydrogens around it. And the electrons are shared evenly back and forth between all of the atoms. Because there's an even sharing, there's no separation of charges, so therefore there's no poles. Lipids and fats have all nonpolar covalent bonds. So what I have here is a saturated fat, and in this saturated fat there are bonds between carbon and carbon, carbon and hydrogen, carbon and oxygen, but all of these bonds is nonpolar, which means that lipids are nonpolar, which is different than the chemistry of water, which is polar. The takeaway here is that polar compounds like to mix with and be with other polar compounds. Nonpolar compounds like to be with and mix with other nonpolar compounds, whereas polar and nonpolar do not mix. Their chemical properties are too different and they repel each other, which is why oils repel water and why they're hydrophobic. So let's take a look again at some more examples of some different types of lipids. I've already mentioned here saturated fats, but throw in unsaturated fats as well. These are types of fats that you've heard of specifically in regard to your foods. And if we take a look at the name first before we dive into their structure, think about what it means to be saturated. Typically when you're talking about something being saturated, you're saying that it's holding as much water as it possibly can. It's soaked. Well, in this case, we're not referring to water. We're referring to, in this case, as hydrogens. If you take a look at this top one and notice the amount of hydrogen in it, it is holding as many hydrogens as possible. Whereas this unsaturated fat right here is missing 2 hydrogens. So because it's not holding as much hydrogen as possible, we consider it to be unsaturated. That happens because of this structure right here. See how there's 2 lines in between these 2 carbons? That's a type of what we call a double bond, as opposed to all of the single bonds that you see across this whole chain right here in the saturated fat. Well, the double bond shares, instead of 2 electrons, it shares 4 electrons back and forth between these carbons, which means there are 2 less electrons for each carbon to share with a hydrogen. So these hydrogens have to be removed in order for this to have a double bond. Double bonds are stronger than single bonds, but they change the shape of these compounds. What's important to remember is as we take a look at these chemical compounds on the screen or on a piece of paper, they appear to be flat. Well, that's not the case in reality. These chemicals are 3-dimensional. They have physical shapes to them. Saturated fats are nice straight chains like this, whereas unsaturated fats have these bend in it like you see here. It changes their geometry. Well, why is that important? Well, when we take saturated fats and we put many of them together, what they can end up doing is stacking on top of each other, one on top of another, so you can fit a lot of them in a given space. Unsaturated fats cannot do that because of this bend. Because of this bend, they don't stack well. So what they end up doing is they end up like sliding past one another, and it ends up making them be liquid at room temperatures. So oils are typically unsaturated fats. Now remember some of the properties of solids versus liquids versus gases. In a solid, the particles aren't moving very fast and they're not moving past each other. They're mostly just vibrating back and forth in place. In liquids, the particles can slide past each other, and in gases, they move freely all over the place. So saturated fats tend to be chemicals or lipids that are solid at room temperature because these chemicals can just stack on top of each other. So you'll find lots of saturated fats in, say, animal fat. So like the fat that you find in butter or the fat that's on like a piece of bacon, right? Now, unsaturated fats, again, are typically oils or liquid at room temperature because they can slide past each other. So like olive oil or avocado oil or canola oil, those would all be examples of unsaturated fats. Now, typically, the ones that are better for you are unsaturated fats, because they don't stack up so much. Saturated fats can lead to elevated levels of like cholesterol, which can lead to heart disease and blocked arteries and things like that. A third type, just to mention as well here, if you take a look at in the elements that make up these fats, they're only carbon, hydrogen, and oxygen, just like carbohydrates. The difference here, though, is that there's not a set ratio of 1 to 2 to 1. There's way more carbon and hydrogen than there is oxygen. A third type of fat are trans fats. Now, trans fats do not exist in nature. These are created by humans when we take saturated fats and then we heat them up at really high temperatures. It then creates these trans fats. So notice that these trans fats have this double bond like we saw in the unsaturated fat, but notice how their geometry is more straight, which allows them to stack. The double bond gives them increased strength, and the fact that they're mostly straight allows them to stack fairly neatly, which makes them really hard for us to digest. Again, these don't exist in nature. There are no living things that have trans fats in them other than us after we consume them. Another type of fat is called the triglyceride. You've likely heard of this before as well. If you take a look at the name and the tri and then the glyceride, if you notice that there are 1, 2, 3 fatty acid chains. This is a saturated fat, there's another saturated fat, and this one is an unsaturated fat, and they're connected together by this glycerol. This is a triglyceride. Triglycerides are used by your body for energy storage, which is one of the major functions of lipids. So if we go on to look at some of the functions, take a look at this flow chart here. In this flow chart, what it's saying is that when you eat carbohydrates, when you eat a meal that's high in carbs, what you're going to do is you're going to get those carbohydrates into your bloodstream. Digestion will take place, and you're going to break apart those carbohydrates, specifically into glucose, and then put it into the bloodstream so it can be carried all over the body. Some of that glucose will be brought into cells and be used to make energy through the process of cellular respiration, which makes ATP. Well, if you have too much sugar in your blood, your pancreas is going to realize that it's going to release a chemical called insulin. Insulin's job is to get glucose out of the bloodstream. And so by doing so, it's going to be moved into the cells. That extra glucose, though, is going to be stored. Based upon our evolutionary past of early humans, food was hard to come by. So if you came by a source of food where there was a lot of glucose in it, you did not want to waste that. You wanted to store it. And the best way to store it is as fat, specifically in this case as triglycerides. So that extra glucose is brought into cells and then stored as fat. That fat will form a type of tissue that we call adipose tissue. Lipids are also used for insulation, as you can see in this lovely image here of the walrus that helps to prevent its body temperature from dropping too low. It resists changes in temperature well, so working very well as an insulator. And a final function of lipids is that they are used to create cell membranes. Now, cell membranes are the structures that completely cover the outsides of cells. We're going to go into more detail on the chemistry of these cell membranes, but they're made of a structure that's called a phospholipid. And there's a phospholipid that's shown right here in this bottom right corner. And they have a unique type of chemistry in them, and that part of it is polar, and the other part of it's nonpolar, which again gives these cell membranes some really, really unique features. We'll dig into the cell membranes, as I said, in more detail later. But for now, I want you to know that lipids do compose cell membranes. And that's it on lipids. And our next lesson, we'll take a look at in more detail proteins.